Hey guys, we're back here to start our unit on ions and ionic bonding. Let's remember that the group numbers represent the valence electrons. The thing you need to remember is that the group numbers help you determine the ions, the charge of the elements in each of the groups. And the last thing you need to remember are where the metals are and where the nonmetals are. Very, very important. How are we going to make chemical bonds if we don't know where the metals are and where the nonmetals are? So we've already talked about the octet rule also. Remember, atoms are most stable when they have 8 valence electrons. They do this to try to achieve Nobel gas electron configurations. So metals give away their electrons and nonmetals gain electrons. At the end of the day, this is what happens. This is why chemical reactions occur. So let's take a look at how ions form compounds. We're going to do this by a little thing called Lewis dot structures. We're going to use dots to represent valence electrons, and we're going to watch to see how they're transferred from one atom to another. Okay, let's look at an example here. Let's take two elements that we know about, sodium and chlorine. Sodium is in group 1 of the periodic table, so we're going to draw one little dot to represent its valence electron. Chlorine is in group 17, so that means it has 7 valence electrons. So let's draw in 7 valence electrons here. I'm just going to space them out evenly, trying to keep them in pairs. Okay, not super important. Just make sure you have the proper amount. Sodium has 1, chlorine has 7. So, as mentioned before, metals, here's your metal, are going to transfer electrons to the nonmetal. The nonmetal here is the chlorine. So here's how it happens. Chlorine has 7 valence electrons, sodium has 1. It's going to transfer it over, and we're going to draw it like this with a little arrow indicating that it was transferred. Chlorine now has 8 valence electrons. This one came from the sodium. 1, 2, 3, 4, 5, 6, 7, 8. Sodium has none on its outer shell at this point. Now remember, if we did an electron configuration of sodium, 1s2, 2s2, 2p6, 3s1, that was normal sodium. But once it gives its electron away, this layer goes away. It no longer has that. So now its outer layer has 8 valence electrons. 2 from there, 6 from there, 6 plus 2 is 8. Level 2 is the highest level. So you see, when metals give away their electrons, it gets them down to an energy level that does satisfy the octet rule. Once chlorine gains an electron, it had 7, now it has 8, its octet rule is satisfied. So now we can write the chemical formula for this. We have 1 sodium for every 1 chlorine. This is our formula. We call this a formula unit. It is the lowest whole number ratio of how atoms come together. Formula units are about ratios. So let's take a look at another example here. Let's take magnesium and let's take some bromine. Now remember, you're going to take a whole bunch of magnesium, millions and millions of atoms. You're going to take millions and millions of atoms of bromine. You're going to mix them together to make them form an ionic compound. So let's start off with our metal over here. Magnesium is a group 2 metal, therefore it has 2 valence electrons. Bromine is in group 17, so it has 7 valence electrons. Let's draw 7 dots. All right, so the metal is going to transfer to the nonmetal. There it goes. So now bromine has 8. But the problem is magnesium still has 1 left. So what are we going to do? It's got to do something with it. We need another bromine. Let's start off with 7. Here it goes. Here comes the 8th one. Boom. We're done. Bromine has 8 valence electrons everywhere. Magnesium is done. It gave away its outer shell electrons. We're finished. This is our ionic compound. What's our formula unit? Mg, because there's only one. Br, how many Brs are there? There are 2. MgBr2, magnesium bromide. We'll talk about naming soon. But remember, this is just a ratio. When we're doing these ionic compounds, this is a ratio of atoms and how they form. Okay, let's look at another example, slightly trickier. Let's have some aluminum and some oxygen. Let's start off with the valence electrons. Aluminum is in group 13, so it has 3. 1, 2, 3. Oxygen is in group 16, so therefore it has 6. I'm going to draw 6 dots. And let's play this game. Metal is going to transfer its electrons. So oxygen had 6, now it has 7. Here comes number 8. Okay, oxygen's done. It now has 8 valence electrons. But we still have one more to get rid of. Or where's it going to go? It's got to give it to an oxygen. Remember, we have millions and millions of atoms here, so we need another oxygen for it to hook up with. Let's start off with 6 valence electrons, because that's what they start with. All right, they react. Here it comes. Here comes electron number 7 for the oxygen. Okay, the aluminum's empty. Its outer shell, all the electrons are gone, but we still need one more here. We only have 7. We need another one. So what do? Another aluminum comes along with its 3 valence electrons. One of them is going to transfer to this one. Boom. Now it has 8. But we still have 2 more here to do something with. What's going to happen? We need another oxygen. Start off with 6, because they all start with 6. Let's transfer metal to nonmetal, metal to nonmetal. There we go. 1, 2, 3, 4, 5, 6, 7, 8. Aluminum's empty. Aluminum's empty. All these have 8. We're finished. This is the formula unit. Aluminum, there's 2 of them. Oxygen, 3. Again, this is a ratio. For every 2 aluminums, there are 3 oxygens that are going to hook up. Now remember, this is happening millions and millions of times inside your beaker. Very cool. Okay, so we have to remember that formula units represent the smallest whole number ratio of ions. Here we have some examples. NaCl, it's a 1-to-1 ratio, so the only way to write that is NaCl. There's no other way. Sometimes you may end up doing a dot structure and you're getting larger numbers, like look at Mg2O2. You could end up with something like that, but it needs to be reduced down to its lowest whole number ratio. What if you do a dot structure and you end up with Al4O6? That gets reduced down, Al2O3. These don't really represent the number of atoms in a molecule. These aren't molecules. These are called formula units, because what ends up happening is that these compounds make ionic crystals. It's simply a ratio of how many of each atom there are in these crystals. This is what a typical crystal of one salt particle looks like. Notice there's many of them. But the formula unit for this is NaCl. For every 1 sodium, there's 1 chlorine. But this is how they hook up together. So here's some more pictures of some salt crystals. Look at the squareness of them. This is how they bind together at their atomic level. You just have to remember that even though there's many, many atoms in one crystal, the formula unit is still the same. It's nothing more than a ratio. Here is an example of some minerals that are found in the earth. If you go to museums, you'll see these. But notice how these are all ionic compounds. They're all metals bound together with nonmetals. Look at the beautiful shapes that these crystals make. This is a clue to what they look like at the atomic level. Remember, they're binding in these certain ratios. Okay, and finally, we'll just mention here some properties of ionic compounds. First thing you need to know is that they are water soluble. They dissolve in water. Not all of them, but the majority of them do. Things that, like minerals and rocks, they obviously don't dissolve in water. Otherwise, when it rained, we wouldn't have any anymore. But for the most part, ionic compounds are water soluble. They also conduct electricity when they're dissolved in water or they're melted. The ions need to be free to flow. It won't work if they're in a solid form. You can't take a conductivity meter and just stick it on a pile of some salt. It's not going to conduct electricity. You need movement there. You need the ions to be moving around, and they will only move around if they're in water or if they're melted. Okay, you should also know that ionic compounds have very, very, very strong attractive forces. They are the strongest bonds that we're going to talk about in chemistry. Because of this, they have very high melting points. Look at sodium chloride. The melting point is 800 degrees Celsius. That's about 1500 degrees Fahrenheit. Very, very high. That tells you that the bonds between the sodium and the chlorine are very strong. You need a lot of energy to break those bonds. They are typically solids at room temperature. So why are these forces so strong? Well, it has to do with the charges these atoms obtain once they gain or lose electrons. This positive-negative force causes an attraction. These are called electrostatic forces. When opposites attract from a positive ion and a negative ion, when they come together, they are held very, very tightly. This is why these bonds are so strong. Okay, that wraps up our first lesson on ionic compounds. See you next time.